Good afternoon. Thank you, everybody, for coming to our presentation today. My name is Gary Osmond, and with me today is John Castronaro. We're going to do a presentation for you today dealing with air vapor barriers. In particular, we're going to take a look at the permeability of air barrier membranes and what does this mean to you. Albeit in our building envelope systems, certainly the function of the exterior wall takes on a number of different types of objectives. The first, of course, has got to be structurally sound. It needs to be durable. It's going to be taking a lot of wind and rain abuse for the rest of the life cycle of the building, which is really a good place for us to start off in considering this type of presentation. When you folks are looking at the durability and longevity of walls, what's my kind of timeline you guys are looking at? 70 years, 150 years, forever? So when we take a look at these last 2 points of being structural and durable, it's because we're expecting to build buildings that are going to last a very long time. Throughout all this, we're seeing that the industry in itself is doing a lot in regards to creating an environmental separator between what's happening inside the building, where we spend a lot of money to heat and cool the air we breathe, as opposed to what's happening on the outside of the building, where we're going to see varying degrees of temperature differences. To accomplish this, air barriers are incorporated in these types of walls. They're used to improve or limit the amount of air movement that will happen through a wall assembly, and in combination with insulation or thermal barriers, they will improve the energy efficiency of the building through the building envelope. Air barriers in themselves also take on a number of different types of objectives. They need to be continuous. I'm sure you've all seen the little diagram where you start your pencil at one point and you've got to be able to go all the way around. You've got to seal through different types of penetrations, window openings, different types of connections, connect to the roof, of course, connect to the foundations. It's a continuous system. The air barrier needs to be durable, but a little bit different than the first side, because these membranes have to undergo what's happening on the job site for the duration of the construction phase. So they need to be tough and durable and be able to take the different abuse that happens when the different contractors show up on the job site. So durable, strong material, and of course resist the passage of air. Due to the optimum location where air barriers should be considered for proper placement, and there's certainly a variety of locations where you would see it, but your most optimal location would be on the sheathing board. So once we've placed the air barrier in this location, it takes on a few different types of performance requirements. So certainly, the air barrier has to act as the water barrier. It needs to be water resistive. Different membranes, based again on their location and the location of other materials, be it insulation, there's a permeance characteristic, which is what we're going to be talking about today. I'd like to offer you the comment that in terms of permeability, membranes can be vapor open or vapor closed. So either vapor as a gas can pass through them, or vapor as a gas is stopped from moving through the assembly. Membranes, again, because of location, also have to have nail sealability characteristics. And in some cases, there could be requirements for fire durability. They don't want to be adding to the overall propagation of flame. And they have to be compatible with other stuff. Window frames, ductwork, different types of sealants, flashing membranes, all the different things we're typically going to, of course, see that happens throughout the life of the construction of the building. So this presentation is going to take a little bit of a look at what could be the perfect wall, but it's more of understanding where are these membranes intended to be applied as we take a look at the wall. So I've got 3 walls, and starting from your left-hand side, and the differences in these 3 locations is that in this wall here, all the insulation is placed outside. In this wall assembly here, all the insulation is inside the stud space. And in this last wall, all of where the insulation is a combination of being in the stud space and in the cavity. So for our first wall, the optimum location for your air barrier is going to be immediately behind the insulation. In this regard here, again, with all the insulation inside the stud space, this is your air barrier, but the difference between these two This needs to be a vapor closed air barrier. This would be a vapor open. And in our last assembly, where I have a combination of insulation, the air barrier needs to be a vapor permeable type product. So this makes for some very confusing type of construction based on what your design is and how you want to accomplish it. So in today's world of building and looking at the way walls are to perform, we've undertaken this requirement that walls should follow some basic pressure equalized Rainscreen concepts. So in that regards, we're really concentrating on one element of the environment, and that is the rain. We're trying to ensure that with the placement of our air barrier, it becomes an effective rain barrier. So it's stopping the movement of air, but at the same time, this becomes your secondary plane of controlling water. That includes air barrier technology, which includes all of the associated systems and products that would go with it. So with liquid applied membranes, you need sheet transitions. With sheet goods, you need liquids to fix seals, fix cuts, do a weather seal around different types of penetrations. But this systems approach is what has to happen for the continuity of the air barrier to be wrapped around the entire building. And although we're talking about walls and air barriers, there are a lot of building materials within the assembly and the roof that is going to act as that air barrier. It's just a matter of making sure you understand and everything is properly connected. New code requirements, SB10 and SB12, is pushing that a lot more insulation to be placed on the outside of buildings so that we have this. Let me start from the beginning of the slide again. So what we're trying to talk about today is the fact that as we build these walls, there are a number of things that come into play. One of them, and one of the first items, is knowing the placement of where we're going to be placing our air barrier. We're incorporating the concepts of pressure equalized Rainscreen. And that is a system or a program of understanding. We have a lot of bulk water coming through your wall system. Our air barrier located in this position here becomes the ideal location for your rain barrier. So that's the pressure equalized Rainscreen. Moisture is going to come through, can't penetrate any further. Due to air pressures, we see a lot of drainage. That incorporates all aspects of air barrier technology with the different membranes, your sealants, mastics, connecting to other materials, connecting to other assemblies, exhaust ducts, windows, door frame openings. Any type of opening in the wall has to be sealed and connected to the air barrier. Changes to the code dealing with continuous insulation are SB10 and SB12, and they're looking that we try to do something more with insulation layers so that more insulation is on the outside, which is a conversation of understanding relative thermal resistance versus actual thermal resistance. But in all of these cases, considering is this to be a permeable or non-permeable membrane seems to become the confusing part, because we need to cover off two different sources of water. Water which is environmentally coming from the outside, and then this presentation is really going to take a look at what's happening inside the building, what is that other source of water, and how are we controlling it. So when we look at air barriers and whether they be permeable or non-permeable, it's all about location. Location, location, location. And it's the location of the insulation that wraps around it. The sources of water we need to take a look at from the exterior is rain and melting snow, happens seasonally. But this presentation wants to take more of a better look at permeability of materials, and that deals with vapor from within the building trying to make its way out. And the sources of that water is, of course, the construction process itself, pouring concrete, bringing in new materials, painting walls, putting down type of liquid membranes intended for the structure, but by far they provide a lot of moisture. Occupants and uses is the next item that's going to have a major role on how much moisture is inside the building in itself. Because what ends up happening seasonally every year is that it gets extremely cold outside. We don't live that way. We live in an environment where we increase the temperature and we would arbitrarily increase the interior relative humidity. And when there's a difference between the relative humidity inside a building as opposed to what's happening outside of the building, you're going to get a vapor drive, and moisture is going to want to come from within the building and come out and get past these membranes. So it's vapor as a gas that's inside the building needing to find its way out. If you take a look at this graphic that we've got shown here, there's a number of different types of building materials. This is our Super Seal stick VP on the wall here, over top of dense glass gold, so we can understand there would be insulation inside the stud space, insulation inside the cavity, marking this as a permeable material. But we've got this big hunk of concrete here, we've got lots of glass. So throughout the building structure, the materials that we would attach to have both the opportunities of being either a non-permeable type product or permeable, and some of those we don't have a decision on what they're going to be because of the nature of the beast. But we're still stuck with this issue that there's vapor inside the building that has to get out. So permeance, or the measurement of these materials, so it's permeance that qualifies the rate of vapor diffusion. How fast will it come out of the wall? Permeance is expressed as a rate of vapor diffusing through material as a function of time per unit area where there's a vapor pressure difference. And it happens every year. It gets cold outside and we heat inside. Or it gets extremely hot outside and we cool inside. So we always get that vapor pressure difference. Moisture is either trying to push itself out or is always trying to suck its way back into the building. Let's be clear, very clear on some terms that are being used, sometimes incorrectly. Low permeance materials are vapor retarders. Type 1 vapor barrier, type 2 vapor barrier, as they're mentioned in the building code, are actually vapor retarders. They allow vapor to pass through the wall. A type 1 is 15 nanograms, a type 2 is 45 nanograms. So consider a nanogram the tip of your pen. So on a daily basis, per unit area of wall, per unit time, you've got 45 tips of your pen, bits of moisture, allowed to get through the wall. So those are low permeance materials. They're vapor retarders. They allow moisture to get through. And that's the moisture we have to contend with. High permeance materials, which are typically the air barrier programs, anything above 10 perms is considered a high permeance vapor permeable material. No permeance means no moisture gets through. And Suprema makes a number of thermal fusible or self-adhered membrane, a little bit more stronger, durable than our Super Stick 1100, but those materials do not let any moisture pass through. And you would make these considerations on which one to use and where based on the end of the day intended use of the building. Is this a residence? Is it a student residence? Is it a hospital? Is it a swimming pool? Is it a museum where you're not worried so much about vapor diffusion? In a swimming pool and a museum, you're worried more about maintaining a certain vapor load. So in those cases, you would look at materials that have no permeance. So considering all this, there was some testing that was done. What we know for sure, walls get wet. It rains or we have a vapor drive. The question becomes, can they dry out? We know different materials have the ability to allow it to pass through, but sometimes we're finding that it's other assemblies beyond the air barrier or inside that is going to have more an effect on the permeance of the wall than the permeable air barriers themselves. Higher permeance materials certainly equals lower drying or shorter drying times. But we needed to know what is that time and what is the rate. So a lot of testing was done to try to clarify that, and that's what the rest of this presentation is going to take a look at. So a lot of testing was done by Suprema to try to take a look at what's the acceptable or what is an appropriate vapor permeance rate of different materials, and we did all this as a measurement of time for vapor diffusion to occur. So in the test samples, there was a number of blocks of wood, sorry about that, fully saturated, and then wrapped with an air barrier material. Now, the materials that were selected had varying degrees of vapor permeance, known various vapor permeance rates. So we knew we were playing with a number of different materials. Samples were put into an established environment where we can control the moisture, and then the test method was run through. This graph represents the summation of all the test criteria. And what we're seeing in reading the graph is that if we have a membrane that has a water vapor permeance 10 to 20 perms, you're going to see the bulk of the water escaping or equalizing. In the test, it was referred to as normalized. So consider this block of wood wrapped in a bag. How long does it take for the moisture to escape? And what was found is 90% of the moisture can easily escape with a 10 perm product. So 10 to 20 does the job. There are materials on the market with higher permeance rates, but at the end of the day, we're seeing that only contributes to being about 8% faster than the other materials. So there's not a lot of value in saying I have to go with something extremely high in terms of permeance from the ASTM E96 standard, which tests the permeance materials. There's 3 classifications, and the third one is 10 perms. So 10 perms is a realistic value for a membrane to have to get appropriate amount of drying time or drying rate. We went on and did a little bit more modeling using WFI. Is everybody familiar with the WFI program? It's a computer simulated program where the design professional adds in the data he's looking for on the wall assembly, the use of the building, and the geographic location where you're going to be building your building. So for the next hour, we're going to go, I'm kidding, it's just 5 minutes. So we did do a lot of testing for all the different regions, but we're just going to give you a summary of what was done and go on with the demonstration. Important to know, though, when you do a dew point calculation or where you do these WFI calculations, there's a known variable, no air leakage. So all of this is about vapor permeance on the premise that there's not air pressure pushing moisture through the wall. This is simply a measurement of vapor diffusion with no air leakage. So in the modeling, the simulations were to take a look at the drying time of different wall assemblies. The moisture content of the sheathing board used in the assembly was increased to 28%. And what we were looking at is the time to take that board to go down to 20%, which is normally what we see in buildings. So again, this is taking a look at the drying time required. The simulation started in the beginning of the year, February, and we ran it up to a full year using different materials in the assembly to get a good calibration of what is the right number. Excuse me. In this graphic here, we're showing you one of the wall types, which is brick insulation, our air barrier, an insulated stud space. So the cavity and the stud space is insulated. This needs to be a permeable membrane. The other sample is a sheathing board, a clapboard, or a cement board on the outside. Here's my air barrier, my plywood that was brought up to 28%, and the rest of the assembly. If you get a chance to come by our booth, we get more time to talk to you. As we went through the study, we referred to this as non-insulated cladding, and this is insulated cladding. So this is the 2 models that we sent through the WFI program. And what we found is that membrane permeance above 10 perms had less impact on the design than the type of cladding and the type of insulation. So those have a significantly greater impact on the assembly in itself, on its ability to dry out more than, do I need something at 75 perms or am I good at 8 perms? Adding a permeable insulation certainly allowed drying to occur at a faster rate. But the test also had shown us that membranes with higher permeance rate, because this was run for a year, so we have the winter vapor pressure drive to the out, and then the summer vapor drive to the in. right? So it was over the full year, and what was found that materials that had a higher permeance rate had a greater ability that vapor would do reverse drive and come back into the assembly. So at the conclusion of all the testing, several things were clearly understood. Wetting and drying characteristics of a wall assemblies is complex. Based on the different cladding types you may consider, the assemblies, steel stud, wood, use of the building, elevation of the structure, a number of things. Air barriers and whether they're permeable or not permeable is not that complex. Your details can be, but the simple physics of which one to choose becomes a lot clearer. When considering these membranes, you need to take a look at the whole assembly and ensure that you're not pushing for one type of permeance on the membrane only to have materials installed on top of it that will in fact act as a vapor barrier. Again, high permeable membranes seem to have a negative effect where there's the ability for more moisture to come in at different times of the year. So all of these certainly have less influence than, again, the permeance of the building material itself. And, I think I repeated my last line up here. So with that, Supreme's come up with a number of different materials that we're going to demonstrate for you. This product here, which is on our sample board here, is Sopraseal Stick VP, a self-adhering, water-resistive, vapor-permeable air barrier. So self-adhering in terms that on the backside we have the typical release film and then a PSA or pressure-sensitive adhesive. This is significantly better, or different rather, than our, here it is, other membranes you may be more familiar with the black gooey compound on the back. So this is our Sopraseal Stick 1100, which is a self-adhering, non-permeable air barrier. So differences. We typically see these types of materials used on walls where all the insulation is on the outboard of the building. These need a primer. This product here does not require a primer. We have some samples here. We're going to show them around later. But what we'd like to do at this point in time, certainly, absolutely. Feel free to take 5 or 6, hand it out. Kidding. I have somebody do that. So what we're going to do for this next part of the presentation, so I'm just checking my time. What we're going to do for the next part of this presentation is that my colleague here, John, is going to run through some very basic steps on how these materials are to be installed. To start off with, membranes come 3 feet wide by 100 feet long in a roll. The contractor can easily clip it off to a manageable size. And what John and I would like to show you here is that there is a proper way of pulling the release film off. And it is typically a 2-man job just for its sticky material. But you pull the release film down as opposed to trying to pull the membrane off the release film. So if your contractors are having a rough time, they're just pulling the release film off at a different rate. In a typical installation, one may score the membrane, remove the first top 4 inches, stick it to the wall, and then pull it down, which is where we're going to start off this part of the demonstration. So what John has already done is we've removed the top 4 inches of membrane so that we start to get our adhesion at the top. He can line the membrane up. You can lay the membrane out and then simply pull the release film from the underside. When installing air barrier membranes, it's always important that you basically start from the center, move your hands out in 2 directions to avoid those nasty wrinkles. You can see John is able to easily pull the membrane off. PSAs are different than SBS modified membranes. You have an early green strength to the material, meaning the contractor will do his best to align the material to where it's supposed to go. If there is an error, there's something in his way, it is a membrane that can be easily removed, replaced back on, and then you, as a contractor, can finish to remove the release film, keeping it nice and straight. The next critical, very critical issue of all membranes used in air barrier technology is that they need to be rolled, whether this is an SBS modified membrane or the new PSAs. We refer to all of them needing the pressure. This is a PSA, pressure sensitive adhesive, where with the Super Seal Stick 1100, the black on the back, that's a pressure sensitive membrane. You use a primer. The primer leaves residue on the substrate as the water or solvents evaporate, and then the membrane sticks to the primer in itself. Any questions? Oh, come on, we can't be that good. What John and I would like to do now is we're going to hand around a few samples. And certainly feel free. You sure you want to see that? That's right, you don't have SBS, so you can see one of those. So, sir, what we're trying to show you, you can see there's peel tests and then there's pull tests. And that's what the tabs are there for. So there's different ways of taking a look at the way these membranes react after they've been installed. So with these types of products, without the use of a primer, we're able to take these membranes and stick it to concrete, stick it to dense glass gold, stick it to a number of substrates without the aid or use of a primer. When we take a look at SBS modified membranes, everybody can clearly see that there's an advantage that if a mechanical fastener had to go through the membrane, it's the material on the back that will seal around the shank of the fastener and cause it to seal. With the PSAs, it's the way the membrane in itself is being used that we can still put a fastener through it without water penetrating through. So we can meet the objectives of nail sealability with the new PSAs as well as we can with the Stick 1100. Any other questions? Please, by all means, come to our booth. We're just over at 1125. We have more information, and we'd be more than happy to go through the test in itself or any of our other great materials. Thank you very much.